Hi, and welcome to this session BP1281, SUSE Rancher and Kubernetes Secrets use case, how to encrypt your data in the cloud. I'm thrilled to be your host for today, and during the next 30 minutes or so, we're going to be talking about key topics when adopting a multi-cloud or hybrid cloud strategy around privacy and end-to-end data encryption. So the talk is going to be focused around Kubernetes because it's perceived as the de facto cloud operating system that allows you to keep a cloud agnostic strategy across the board. Because as soon as you're running Kubernetes, then you can run it anywhere and use the same strategy, the same technique to encrypt your data regardless of the location. And so for this, we're going to be starting by taking a look at secrets in Kubernetes, what they are, what are their characteristics, their caveats. Then we're going to take a look at how to encrypt your cloud native data, so the data that you are using in Kubernetes, by using Kubernetes native paradigms, because as soon as you deploy Kubernetes and start using it, you want to keep as much as possible. You want to keep tools within Kubernetes so you can keep this kind of agnosticity for your tool set across many different environments, many different clouds. Then we're going to be introducing Trousseau, an open source project that will allow you to use any external KMS provider and make it operate the Kube native way. So in that particular instance, we're going to show you how to integrate it with SUSE Rancher, and then we'll conclude by a demo. So let's get started. My name is Nick Vermande. I'm a principal developer advocate with Ondat, and I've been working with Kubernetes for approximately the past 6 years in various companies. So Cisco, mostly working on the CNI, Container Network Interface, and nowadays with Ondat more focused on the CSI, Container Storage Interface, and the corresponding data services. So in our first topic, let's take a look at Kubernetes secrets. There are different ways to store application data in Kubernetes. As you know, when you migrate or create a new application, develop a new application within Kubernetes, you're not supposed to hard code application parameters and contextual data. You should use Kubernetes primitives to do so, and there are a couple of them that will help you. So first, ConfigMaps. So ConfigMaps are key value pairs that you can mount in Kubernetes as volumes for your pods or as environment variables. Then you have obviously data that if you want to store data for a particular application, maybe a stateful application, then you can use Kubernetes volumes that will make use of local or remote storage disks. Then we have what we call the downward API. So the downward API gives you this ability to add specific container and pods field into your manifests. So for example, you may want to dynamically inject the IP address of a pod or any sort of dynamic contextual information that you want to make available for your containers. You can use the downward API. So again, downward API, you can use it as environment variable or you can mount it as volumes. And finally, we have secrets. So secrets on paper, they really look like ConfigMaps, but with a few differences. Let's take a look at them. If we look at ConfigMaps on your left, we see that there is a data section where you can find the key value pair. So game.properties would be the key, and then you can find a set of different parameters. Same thing for the UI.properties key. Everything is in clear text and easily accessible. For secret though, you can see there's also a data section with the same keys, but the values are not directly readable. But is it really encrypted? Well, no, it's encoded, which is different from encrypted. Anyone with the proper command line can encode and decode messaging. They share the same encoding properties. So this example will show you how to decode the string that we've shown before, and the content is actually exactly the same as for the config map. So both config map and secrets are not encrypted. The only difference is that config map are in clear text, but secrets are encoded in base 64. So now the question is, should you treat secrets as config maps? And if you want to store sensitive information in secrets, why should you care about your secret security? Well, a couple of reasons. First, any user who has read permission on secrets within a given namespace can read all secrets within that namespace. Right? Anyone with read permission for etcd, which is where Kubernetes is storing all the objects, so including secrets, can read all secrets in the cluster. Right? So you want to get your secrets encrypted in etcd, which is what we are going to focus after. And finally, anyone who can connect to a pod associated with a service account that has read permission for secrets can read all secrets in a given namespace. This is kind of the same thing as the first point, except that a standard user, this is a service account that is used within the container to access Kubernetes objects and Kubernetes control plane objects. So how to remediate these issues? Well, first, apply the least privilege principle for your users, your Kubernetes users. Then encrypt secrets at rest in etcd. Also, you want to secure all the etcd members. So typically, this is all your control plane nodes. So the communication between this member should be using TLS. And then finally, you want to limit etcd access altogether to reduce the attack surface from your control plane by using stateful firewall rules where you can. Now that we have clarified secrets, their challenges, and their importance in Kubernetes, let's take a look at the data themselves and how to encrypt cloud-native data. But when we talk about cloud-native data, what does that really mean? For this, let's take the anatomy of a stateful workload or stateful application in Kubernetes. In that particular example, this is a Redis database. So at the foundation, when you want to deploy a database or any stateful workload in Kubernetes, you will use a dedicated controller, which is a stateful set. So that's a first-class citizen object in Kubernetes, which has a couple of properties. So every pod member of a stateful set will have predictable names starting and ordinal numbers starting with 0. So for example, here with a 3-node cluster for the Redis leader, you would end up with the first pod, which will be maybe Redis leader -0, and then the second one -1, -2, etc. What is very particular to stateful sets is that the way they provide storage and volumes is different from traditional pods. So with a stateful set, you have a particular statement, which is called a volume claim template, that allows you to provision individual PVC, so persistent volume claim, as well as persistent volume on a per pod basis. So every pod, and in turn, in that case, every Redis node will have its own individual volume. And typically, how you provision volume in Kubernetes is via a dynamic storage class, which is one of the most common way, and one of the most simple way to provision. And by just defining your storage requirements and specifying a storage class, and creating the PVC the backend volume will be created automatically, right? So in the end, you end up with what is displayed on that screen. You have the storage class that is managing the storage provisioning for a particular set of pod as part of the stateful sets. You create your PVCs, you link the PVCs to the storage class, and then by creating this link, Kubernetes will know that this is a particular storage backend that is going to be used and bound to the various pods. And basically the storage class is where you want to enable extra features. So by default, encryption, replication, compression, caching, all these data services are not available in Kubernetes by default, right? So it means that you have to use another component, an external component to provide these services, including for encryption. And at the beginning, the various storage capabilities can be plugged into Kubernetes by using what we call Kubernetes CSI, or the Container Storage Interface. This is a standard that has been defined for storage plugin back in 2018. And before that, Kubernetes used to have the storage drivers included in the core code, so in tree. So Kubernetes moved away from this model to define APIs and RPCs that enable dynamic provisioning and deprovisioning of a volume, attaching, detaching, mounting, unmounting, creating and deleting snapshots, as well as provisioning a new volume from a snapshot, so essentially cloning. All of these features are high-level functions that are expected from Kubernetes and implemented by storage vendors. And essentially now, Kubernetes CSI is just another application that you can install onto your Kubernetes cluster. So typically it will be composed of a daemon set, so an agent per node, as well as some control plane components. Then in addition to the CSI basic features, storage vendor may provide additional capabilities and expose this to the user by a particular parameters or label for storage class and PVC. So you can decorate storage class and PVC with additional parameters that will then be synced with the storage provider control plane, and then in turn is going to enable this feature in their own feature set. So for example, here this is Ondat storage class, where you can enable particular Ondat feature by using key value pairs as parameters. So here we have a number of replicas that is set to 2, encryption that is simply enabled by using the Boolean true. Same thing with topology aware, which allows you to spread your replicas across multiple availability zones. On top of this, there's also another CSI, open source CSI, that is called the Secret Store CSI driver, that allows you to encrypt and mount secrets from external KMS provider directly as pod volume. So the secrets lifecycle is essentially managed outside of Kubernetes, and they are not stored directly in Kubernetes, although you can, there's an option to synchronize them. But it does not encrypt objects stored inside Kubernetes etcd. Multiple providers are supported, such as HashiCorp Vault, AWS KMS, Google Cloud KMS, as well as Azure KMS. And finally, also the changes that you are going to make to those secrets in the external store, they won't be reflected in the mounted volume as the pod is running. It's only because it's only sets at pod when the pod is started. So any update, subsequent update, won't be reflected into the pod mounted volume. Ideally, you want the best of both worlds. On the one side, you want to encrypt your secrets within etcd, but at the same time, you want a Kubernetes native way of doing so. So let's take a look at how to encrypt resources at rest with Kubernetes. This is achieved via what we call an encryption configuration manifest, where you specify what resources you want to encrypt, decrypt, as well as the providers. And there are two family of providers, let's say. You can use static keys, or you can use an external key management system to manage the lifecycle of those keys. So using the static keys, obviously, as you can see on the screen, they are displayed in clear text within that encryption configuration manifest, which means that anyone with access to that particular file will be able to decrypt all the secrets that are stored, all the resources that are stored into Kubernetes. So in that particular example, we see that the only resource we want to encrypt is secrets, which is the most common use case, although you could encrypt other object if you wish so. The external key management system has another couple of parameters. So you're going to define the name of the plugin as well as the endpoint, which is the listen address for the gRPC server. So then Kubernetes will be talking to that particular socket process using gRPC, and that particular KMS provider needs to support the Kubernetes envelope encryption scheme, which is using both a data encryption key used to encrypt the data in combination with a key encryption key that is used to encrypt the data encryption key. So this is available for any Kubernetes distribution, but if you need a more secure distribution, SUSE Rancher provides RK2, the next generation Kubernetes engine, also known as RK Government, which provide a couple of extra security features and will pass CIS 1.5 and 1.6 benchmarks by default. So it is an upstream conformant Kubernetes distribution, cloud provider agnostic. You can install it in any cloud, you can install it on premises, and the overall management can be centralized with Rancher server. It also supports modern CNI meta plugin like Multus, which allow you to chain multiple CNI if you need multiple interfaces within your containers. It does provide a support for air-gapped deployment where you don't have any internet connectivity. Containerd as a replacement for Docker, which is a good thing since Docker Shim has been deprecated some time ago. Also have compliance with FIPS 140-2, which is a standard to approve cryptographic modules. And finally, it's a very simple install process if you want to do it manually as opposed from the Rancher server. It is aligned with the K3S model, so single binary for server and agent, and then you just join the agent to the cluster. So quite simple. In terms of encryption, etcd encryption is enabled by default in RK2, where RK2 sets on the API server encryption provider config to a specific file where you can find the encryption configuration. However, it does use static keys, which has the issue we mentioned before. So they are in clear text and you need a way to manage potentially rotation of the keys yourself. So how can we solve that particular problem? Here comes Trousseau. Trousseau acts as a KMS proxy between the Kubernetes API server and the backend KMS provider. So if we look at Vault, Vault initially without Trousseau will have its own way of managing secrets for Kubernetes using a sidecar model within the application. So the secrets are not managed within Kubernetes at all. And then Trousseau will allow you to make Vault or to turn Vault into a compliant Kubernetes KMS provider, because now it will use through Trousseau the envelope encryption scheme and will be directly connected to the Kube API server. So it allows you to use external KMS provider, but without the drawbacks of managing them outside of Kubernetes. So the process to encrypt and decrypt secrets with Trousseau is described on the right in the picture there. So first, the user is going to create a secret, and send it to the kubeAPI server. Then the kubeAPI server will talk to Trousseau via gRPC, Trousseau acting as the gRPC server we've mentioned before. Then Trousseau will take that particular request, encrypt or decrypt, and send it to one of the KMS provider that that you will have configured. So today it only supports Vault, but we have other plans to also integrate with other KMS provider like cloud providers, for example. And Vault then will make use of a transit key. So that key is not stored in Kubernetes at all. It is just managed outside of Kubernetes in Vault. And Vault also won't store the encrypted result. So the encrypted secret will be transient in Vault, right? So Trousseau will send the request to Vault. Vault encrypt or decrypt the secret using its transit key, send it back to Trousseau, and then Trousseau will send again the result back to the kubeAPI server. And in the case of encryption, then the kubeAPI server will store the encrypted secret within the etcd store. So how do you configure it with RK2? It's quite simple. The initialization file, the encryption-config.json, should be left empty, and then you change the config.yaml file to point to the new encryption config file that defines how to use Trousseau as the Unix domain socket. And that's enough theory for today. Let's jump into a quick demo. So in this environment, I already have deployed a Kubernetes cluster and created the configuration with Trousseau. And in terms of the storage class, I've got Ondat encrypted storage class that I want to show you. Ondat encrypted. And you can see that here encryption has been enabled. So any PVC consuming that storage class will have its data encrypted, and a secret will be created on a per volume basis within the namespace where the PVC is deployed, and that secret will represent the key that is used to encrypt and decrypt that volume. So I also have deployed a stateful set, a MongoDB stateful set, so a database, a 3-node cluster, and you can see that for every node, so node 0, 1, and 2, I have 2 volumes per MongoDB nodes, one for data and one for logs. And also, as expected, you see that I have 1 secrets per volume. So I've got total 6 volume and total 6 secrets. Now, what I want to see is the secrets unencrypted. So again, if I do, let's use the first secrets here and check that it's not encrypted using kubectl because I'm an admin. Secrets here, there. I should see it unencrypted, right? So I've got the data there. Everything is fine. It's just base 64 encoded, as you can see. Now I want to check that within etcd it is still encrypted by Vault. So for that, I'm going to use the etctl command, and I'm going to use the location of that particular object within etcd and checked the content using an xdump to check what is visible there. And if I go at the very top here, I can see that this is gibberish. Here, this is the text. So it is effectively encrypted. And the proof is at the very beginning here is going to tell you that this is encrypted with a KMS and Vault provider, which is available through Trousseau. So as a result now, all my secrets are effectively encrypted within Kubernetes, and Vault is using its transit key to realize the encrypt and decrypt operation thanks to Trousseau, which is acting as a man in the middle. This demo concludes our talk for today. But just before leaving, I just wanted to highlight a couple of key takeaways that we've been talking about. So first off, secrets are not encrypted at rest by default in Kubernetes. You need to find a way to do it by your own means. And the only way to decouple data encryption from cloud providers is to use a Kubernetes CSI that supports volume encryption. You cannot rely on cloud providers to do end-to-end encryption. And as soon as you're using more than one, then you will have to learn new KMS and potentially new APIs, etc. So using a Kubernetes CSI that supports volume encryption allows you to become cloud agnostic and to keep the same encryption mechanism end-to-end. In terms of Kubernetes distribution, we've seen that RKE2, which is RKE government, encrypts etcd by default. However, it's making use of static keys, which is not ideal. To alleviate this problem, you can use Trousseau, which is an OSS project that delivers a KMS proxy that makes any backend KMS provider Kubernetes native, right? And that supports this envelope encryption scheme that is expected by Kubernetes. I hope you enjoyed the rest of the conference. Take care of yourself and see you soon.